Good morning, everyone. Welcome back. As you can see from yesterday, based off your marks, the quiz wasn't too terrible. So for the most part, you guys did pretty well. Like I said, next week you guys will have the whole week to work on your CPT. This is going to be a package of questions based off all the units we did so far. And that won't include the rates of change. So you wouldn't have to worry about the rates of change on your CPT. So it is safe to say that we will probably finish this unit this week, probably. You will have your Unit 6 test on or assignments on Friday. I'll make it available during the day. So you'll get your updated marks on Friday. I just have to mark your assignments from last unit today, and then I'll give you guys an updated mark on Friday. So today we're going to be talking about evaluating logs. So first of all, we need to remember what we did on, when was it, last week, Friday? So the inverse of the exponential function y is equal to b to the power of x is x is equal to b to the y, which is an exponential form, or y is equal to log b x, which is the log form. So a log is an exponent. The log of a number to a given base is the exponent to which the base must be raised to get the number. So logs of negative numbers do not exist because a negative number cannot be written as a power of a positive base. So for example, we have log of base 4, negative 2. It is not possible because 4 to the x is equal to negative 2 has no real solution. Okay? This is because an exponent cannot give you a negative number. Which means that this number has to be positive all the time. So on a calculator, log x is equal to log base 10x. This is called the common logarithm, which we learned about yesterday. So apart from the properties we learned on Friday, there are some new properties involving logs. So if we have log of base b1, obviously that equals 0, because anything to the power of 0 gives us 1. Then we have log base b to the x is equal to x. So as you can see, the left side is just equal to the exponent. And the last one, log b to the power of log base b to the x is just equal to x again. So as you can see, the right side is just equal to the number that comes after the log. Class starts at 8:20. But it's okay if you're 10 minutes late. I usually don't take attendance till like 9 o'clock anyways. So example 1, we have log base 6, 1. So log of 6 to the 1 is equal to x. Okay, so we need to solve what that value is going to give us. So 6 to the x is equal to 1. What exponent always gives us a return value of of 1? Zero. So we get x is equal to 0, which means log base 6, 1 is equal to 0. The next example we have is log base 3 to the power of 2 is equal to x. But because of our logarithm law, we just know that x is just equal to the exponent. So in this case, the exponent is 2, which means x is equal to 2. Or log base 3 of 9 is equal to x. Okay? And we can say 3 to the x is equal to 9. And we still get the same answer. We get 3 to the x is equal to 3 to the 2. Therefore, x is equal to 2. Okay? But because of that property that we have, all we have to do is look at the exponent, and that would give us our x value. And last but not least, we have 5 to the power of log 525. So we're going to use that property. And all we have to do is look at this number over here at 25. So it is safe to say x is equal to 25. Okay? So all we're doing here is you're just using properties that were given to us and using them to solve the problems at hand. So are you guys fine with the first few examples? So this is the real examples now. So example 1, we want to evaluate with a calculator to 2 decimal places, and we want to rewrite the log statement in exponential form. Okay? So if you just want to use a calculator, all you're doing here is because the log button on your calculator already has the base 10, we assume all of these have a base of 10. So if you plug in log and then the quartic root of 100, it should give you a value. Or you can put log and then 100 to the power of 1 over 4. If someone were to do that on their calculator, what would you get for log base 10 times the quartic root of 100? So this is equal to 1/2 or 0.5. Okay, can somebody do the next one for me? Log base 10, 8. So we get approximately 0.9. And the last one, log base 1050, what would that give us? $1.7. Thank you. So as you can see with a calculator, it is pretty easy to find the values of these logarithmic expressions. Now for example 2, we want to determine the approximate value of log 435, and we are going to do this without a calculator. So what we need to ask ourselves is 4 to the power of x is equal to 35. So we need to figure out some exponent x that gives us a value of 35, okay? So what we're gonna do is make a chart of the powers of exponents to the base 4. So we're gonna start with 4 to the power of 1 gives us 4. 4 to the power of 2 gives us 16. and 4 to the power of 3 gives us 64. So based off these first three numbers, 4 to the 1, 4 to the 2, 4 to the 3, what can we assume about x in our solution? So log 435 has to be between 2 and 3. So now, at this point, we need to take values between 2 and 3 and put it for our exponent. So let's take 4 to the power of 2.5. That is going to give us 32. We're close, but not exactly at 35. So then we take 4 to the power of 2.6, which gives us 36.7. So now, given that information, what can we assume about log 435? So it has to be between 2.5 and 2.6. So our next chance is just to do 4 to the power of 2.55. And what does 4 to the power of 2.55 give us? $34.29, which means we're almost there. So we have to increase by at least 1 decimal point. So our next one is going to be 2.56. And what does 4 to the power of 2.56 give us? Which means it is safe to say that if we do 4 to the power of 2.565, that's going to give us approximately 35. Which means log of 4, 35, is equal to approximately 2.565. So I know it's not the most conventional way to solve for this, but this is the only way you would be able to solve for this question, is taking 4 to the power of multiple exponents and seeing where that number is in between, okay? So it's more of a guess and check kind of solution for this problem, but that's the only way you would be able to solve it. So is everybody good with example 2? Okay. So we're going to solve the following equations for x. Remember, the first one, we have log x is equal to 3. But remember, we need to assume that the base is 10. Okay? So we are not going to use a calculator this time. So 10 to the negative 3 is equal to x, which means x gives us what? So what does 10 to the negative 3 give us? One over 1,000. So 1 over 1,000 is equal to x, which means log of 1 over 1,000 equals negative 3. Now our next example, we have log base 3 of 1 over 81 is equal to x. So remember, we need to write it in the form of y is equal to b to the power of x. So we have 3 to the x is equal to 1 over 81. So we need to figure out what exponent to the base of 3 gives us 1 over 81. So the 10, so whenever log doesn't have a specific base, you always assume the base of log is 10 when it's not given. So for example, in question B, the base is 3 for log, so we have to work with the 3. And for C, the base for log is x, so we have to work with the x. But for the first one, because there's no base given, you always assume it's going to be 10. So for B, we have 3 to the x is equal to 181. So we need to figure out what number with the base 3 is going to equal 1 over 81. So normally, okay, Matthew said negative 4, which is perfectly fine. So 3 to the x is equal to 3 to the negative 4, which means x is equal to negative 4, which means we can write log base 3 of 1 over 81 is equal to negative 4. And now we have our last example. We have log to the base of x of 25 is equal to 2. So who can tell me what the solution to this question is? 5. So we start by saying x squared is equal to 25. We square root both sides, so we get x is equal to plus or minus root 25. And why can we only take the positive 5 and not the negative 5? Okay, but why does the argument have to be positive? The exponents can't give a negative number. So that's why we need to use x is equal to 5, which means negative 5 is inadmissible. So we get log base 5 to the 25 is equal to 2. Okay, so example 4, we have a bunch of, I guess, easy practice questions. So we need to evaluate each of the following logs exactly. So So no decimals without a calculator, and we want to show all of our steps. So the first one we have log base 3, 27. Can anyone tell me what the solution is for that? So remember, we want to use the properties that were given to us today. So you can use log of b times b to the x is equal to x. So we can use log, in this case, log 3. Can 27 be a square root or a cubic root of something? So 3 cubed. So we get log of base 3 times 3 to the 3 is equal to x, which means x is just equal to 3, and that would be our answer for A. So the next example we have is 2 base 2 over 3 of 81 over 6 is equal to x. So we can do it the normal way, where we do 2 over 3 to the x is equal to 81 over 16. So now we need to determine how we can get 81 over 16 to the same base of 2 over 3. But we can't right now, so we can only get it to the base of 3 over 2. So we have 2 over 3x is equal to 3 over 2 to the power of 4. So 3 to the power of 4 gives us 81, and 2 to the power of 4 gives us 16. So how can we manipulate the right side so that it can give us a base of 2 over 3? What would we have to do with the exponent? Make it negative. So we get 2 over 3 x is equal to 2 over 3 to the power of negative 4, which means x is equal to negative 4. And now we have c, which is log of root 2 of base root 2, 8 is equal to x. So all we're going to do is follow the same steps. So we get root 2 to the x is equal to 8. So what we know so far is root 2 to the x is equal to 2 to the power of 3. However, root 2 and 2 are not the same because root 2 gives you a different value from positive 2 in a number. So what would we have to do to the right side to make it a base of root 2? So we can change the right side base to root 2. All we have to do, so we have root 2 over to the x on the left side. We we can have root 2 on the right side, but what exponent do we have to put it to? Well, that's the final answer. But the right side would just be root 2 to the power of 2 to the 3. And then we get root 2 to the x is equal to root 2 to the power of 6, which means x is equal to positive 6. So how's everyone doing with the first 3 examples? Good, bad, kind of good? We still have 6 examples to fix those confused spaces so that you guys are able to understand. So the next one is simpler. So we have log of 4, base 4 of 32 is equal to x. So again, we have to do the same thing. So we have 4 to the x is equal to 32. So how can we write 32 in terms of an exponent with a base? Four to the power of any exponent is not going to give you 32. But what base and what exponent is going to give you a value of 32? Thank you, Yusuf. So we know 4 to the x is equal to 2 to the 5 because 32 can be written as 2 to the power of 5. However, we need both sides to have the same base. So what's the easiest thing that we can do? Would you rather write 2 to the power of 5 with a base of 4? Or would it be easier to change 4 to the x and change that to a base of 2? You want to write 2 to the 5 in terms of the base of 4, but wouldn't it be easier to change 4 into 2 to the power of 2? So yeah, so let's try that one. So we can change 4 and write it in terms of 2 to the power of 2. So we have 2 to the power of 2 times x is equal to 2 to the 5. So now the 2's cancel out. So we get 2x is equal to 5, which means x is equal to 5 over 2. However, we can do it the other way, where we can change it to the base of 4. So how can we change 2 to the 5 into a base of 4? Yeah, so let's just do the or here. or 2 to the 5 is equal to 4 to the 1/2 times 5, which is just equal to 4 to the power of 5 over 2, which means x is also equal to 5 over 2. So as you can see for this question, there are two ways to do it. Both ways give you the right answer. So you guys can decide which way you want to do. If you find it easier changing 2 to the 5 into a base of 4, or you can change 4 and write it as an exponent to the base of 2. So the next one's the easiest one. So we have log base 12 to the 1 is equal to x. So what would x automatically give us? Zero. So x is equal to 0. F is also an easy one if we use the third property from the first page. So we have 6 to the power of log base 6 to the 18. So what would this equal to? If we use the third property on the first page. $18. Thank you. So x is equal to 18. The next one, G, we have log base 5 of root 5 to the 7. We have to change the inside. So instead of root 5, we're going to write 5 to the 1/2 times 7, which is equal to log 5 of 5 to the 7 over 2. And if we use the second property on the first page, what would this equal to? So remember, the answer is in the exponent that we just simplified. So what would the answer to G be? 7 over 2. So x is equal to 7 over 2. So the next one we have is log of 1/2 of base 1/2 32 plus log of base 7 to 49. So what exponent, when we have a base of 1 over 2, gives us 32? -5. So this is equal to 1 over 2x is equal to 1 over 2 times -5. So we know log 1/2 32 is equal to -5. And then we have log base 7 49. So what exponent with a base of 7 gives us 49? So 7 to the 2. Thank you, Bozola and Joseph. So we get 2. So we're left with -5 plus 2, which means this log expression gives us an answer of -3. And the last one, I, we have log base 3 times 9 times the quintic root of 9. So we need to split this up into two ways. So we have log base 3, 9 to the 1, times 9 to the power of 1 over 5. So when we're multiplying numbers with the same base, what do we usually do with the exponents? We're going to add. So when we add 1 plus 1 over 5, we get log base of 3 times 9 to the 6 to the power of 6 over 5. And now we have 3 to the x is equal to 9 to the power of 6 over 5. And how can we change 9 to have a base of 3? So you have 3 to the x is equal to 3 to the 2 times 6 over 5. And all we have to do is multiply an exponent with each other. Because of power to a power, we multiply the exponents. So we get 3 to the x is equal to 3 to the 12 over 5, which means x is equal to 12 over 5. Are you guys still hanging in there? Any questions so far? Okay, we're all good. And then we're going to get into some word problems, and that's going to be it for lesson 7.3. So the number of mold spores in a petri dish increases by a factor of 10 every week. If there are initially 35 spores in the dish, in approximately how many days will it take for there to be 2,100 squares? So the equation was given to you guys, but I have it here. So we have n of t is equal to n0. I'm pretty sure you guys saw this last year in functions. The half-life or double life formula, do you guys remember that from functions last year? Okay, some of you do, some of you don't. You'll probably be doing it in maybe, I think, chemistry, probably, or physics. So these are half-life and double life formulas. Basically, when you have something that grows exponentially, for example, in this case, we have mold spores in a petri dish that grow exponentially. So n with a base of 0, this is your initial amount. And t is the amount of time passed. And because n is given to us in weeks. So we are going to try to solve for So NT is the amount of spores left over. My apologies. And T is the time in weeks. So what we have to do in this question is we need to isolate for T. So we need to isolate for time. So what would our N of T be? How many spores will there be at the end of this whole, I guess, time lapse? 2100. So we have 2100 is equal to, what is our initial amount? $35. So we get 2100 is equal to 35 times 10 to the t. So we're going to divide both sides by 35. So we get 60 is equal to 10 to the power of t. And since we have logs, okay, remember in the first lesson, we can rewrite from this form into log form. So we can say t is equal to log of 10, log of base 10, 60. And when you guys do log of base 10, 60 on your calculator, what does t give you? So you get about 1.78. So you get t is equal to about 1.8. But because our answer is in weeks and we want it in days, what do we have to multiply it by? Seven. So we take t, 1.8 times 7, and t gives us approximately 12.4 days. Okay, now we're going to do our last example. So for our last example, we have another word problem. So the astronomer Johannes Kepler determined that the time d in days for a planet to revolve around the sun is related to the planet's average distance from the sun k in millions of kilometers. This relation is identified by the equation log of d is equal to 3 over 2 log k minus 0.7. We want to verify that Kepler's equation gives a good approximation of the time that it takes the Earth to revolve around the sun. If Earth is about 150 million kilometers from the sun. So we have our equation. Log d is equal to 3 over 2 log k. minus 0.7. So what would our k value be for this equation? Remember, k has to do with the distance from the sun in millions of kilometers. That's k. K would be 150. The reason why is because it's in millions of kilometers. So we have to take 150 million and divide that by 1 million, which gives us a value of 150. So we get log D is equal to 3 over 2, log of 150 minus 0.7. So can somebody do the right side of this equation and compute it on their calculator, please? So what does 3 over 2 times log of 150 minus 0.7 give us? It is going to give us 2.56, which means log D is equal to 2.56. However, we still need to solve for D. So whenever we're not given a specific base, we can always assume the base of the log is 10. So we have log 10D is equal to 2.56. And if we use what we learned from unit 1, the answer is just 10 to the power of 2.56 is equal to D. So if we do 10 to the power of 2.56, what is our D value? Which means that the Earth takes about 363.1 days to revolve around the sun. And we know our calendar dates are always 365 days. So that answer makes sense.